The Kullback-Leibler divergence is a powerful tool for comparing distributions, but it has a fatal flaw. It is not symmetric. This asymmetry makes many calculations impossible and the results misleading. Today, we are going to explore how the Jensen-Shannon divergence elegantly solves this problem by creating a perfectly symmetric measure. To understand the solution, we must first look at the limitation of its predecessor. The Kullback-Leibler divergence measures how one probability distribution diverges from another, but calculating it yields different values depending on which direction you go from P to Q versus Q to P. In 1991, Jianhua Lin introduced the Jensen-Shannon divergence as a superior alternative. It elegantly solves both problems of asymmetry and unboundedness by measuring how much each distribution diverges from their average mixture, creating a truly symmetric measure. The mathematical magic happens because it defines the divergence via the average KL divergence from the mean. By taking the square root of this value, we get the Jensen-Shannon distance, which is not only symmetric but also bounded between 0 and a constant. This symmetry transforms an unbounded metric into a robust tool for model selection and clustering. Unlike KL divergence, which can explode to infinity when distributions are disjoint, JSD always returns a finite value, making it safe for all probability comparisons. Because its square root forms a true metric satisfying the triangle inequality, it allows for rigorous mathematical analysis in machine learning. This property enables advanced formulations including quantum and generalized variance to offer robust tools for learning under noise. In summary, while KL divergence is unbounded and asymmetric, Jensen-Shannon provides a bounded symmetrization. It quantifies dissimilarity by measuring the total Kullback-Leibler divergence to the average mixture distribution, effectively bridging the gap between two complex datasets. Understanding symmetric metrics is crucial for modern machine learning algorithms. What other limitations of KL divergence have you encountered in your research? Let me know in the comments below.